So they just gave me that feedback today. It's a lot of the same stuff I kind of expected. As far as some of the things for recommendations, one of them was like more space in the test to answer. I've done, because it's 20 questions instead of 25, I am able to kind of double space between each question, so that gives you a bit more room. I would like to add even more room, but it comes to the downside of the more space I give, the more papers I have to print. So that's kind of my limitations. So there is a bit more space. And something I've done for this test is the last page with the equations will be your kind of scratch sheet as well. So the last paper, you already have a scratch sheet that comes with the test. And then throughout the problems, there'll be a little bit more space just due to having less problems and how I've kind of tried to move things around. A lot of it is navigating. Every extra page that goes with the test is 220 extra pages that have to be printed. So that's why currently the test is 4 pages, which sounds intimidating, but it's literally the first 2 pages, front and back, is just the multiple choice. The next 2 pages are the free response, 1 for each. 3rd page is the Scantron, 4th page is the equations, and then extra space. So there's that. Time-wise, the tests have been made. They have been sent to the printer, which is the physics department. So I've sent those along, and I've done my best to reduce the complexity of some of the problems after I solved through it all. I kind of modified them to take a little bit less time. I'm optimistic. I'm optimistic about it. Currently, kind of my thoughts as far as how you all should manage your time on the test is I recommend you spend like up to 60 minutes on the multiple choice and then the remainder 20 minutes on one of the free response. Feel like that's a good kind of allocation of time. Of course, if you finish the multiple choice earlier, then it gives you more time on the free response, but I think it works out pretty well timing-wise because there is only one free response. 20 minutes should be sufficient time to solve one of those. Yeah, let's just leave it like that. So, there's that, test in a week. Today we're going to finish up the last little bit of content. There is one more equation we need to introduce, and then otherwise, really what we're doing today is we're going to be practicing Lenz's law, which is kind of the last scenario where we're going to have to use right-hand rules. So, if you all have challenges on the test, I expect those challenges to mostly be with the right-hand rules. That's what I've seen so far. So what are my recommendations as far as preparing for those problems? My recommendations for preparing for the right-hand rule problems is do these. So in the problem sets, there's a whole bunch of examples here. Look at these without the answers nearby. Just kind of like, these are kind of like the flashcard versions of problems. Quickly go through them. Can I find the force on the current in each of these scenarios? And then up here we have, can you find the force on a moving charge in each of these scenarios? One of the caveats I want to remind you all, these are all positive charges. You do need to remember that negative charges will do the opposite. So don't forget that rule. When we get to the note card, I'll remind you of that. So these are great practice for the right-hand rule number 1. And then when we scroll down to, okay. There's unfortunately no kind of quick ones here. I've done a few in the PowerPoints. I'll probably send out something today or tomorrow, just some, hey, find the magnetic field here due to a wire, and I'll give you some answers, just so you can have some quick, easy ones to practice. But if you've gone through these problems, every single one of these problems basically makes you find the direction of the magnetic field, except a couple solenoid ones at the end. All these ones in the beginning, every single one is great practice for finding direction of magnetic fields. Definitely make sure you're comfortable finding the magnetic field due to 2 different things or more and adding up them together. And there's a few problems here about that. This one does that. This one does that. That one doesn't. This one does that. There's been a good few. So at the end of class today, I'll probably just make a big thing of, hey, here's the important things you need to be studying over the next week. First, though, we got to get through the remainder of content. Reminder to you all as well, the good news I told you all last time is the announcement. No discussion section this week, no grade for it, because I haven't gotten the problems yet. Have I gotten them yet? No. It's outside of my control. Good news, I expect to get them by the end of this week. If I don't, that'll just guess me. We'll get there when we get there. if we get there. So let's go ahead and remind ourselves what we did last time. Last time we just talked about Faraday's law, which says that as the flux is changing, and the flux is this BA cosine theta, as it changes with respect to time, we get voltage. We call it a fancy word called EMF. It's voltage. I need to call it EMF because that's what we call it in physics, but at the end of the day, that's what it is. It's just voltage. I then said, hey, if you have multiple coils, you multiply by that. If you have 500 coils, then it's going to make the voltage 500 times bigger. So we chucked an in front of it, and that's where we kind of left things. We did a problem where we found the flux. We did a couple problems where we found the flux. And let's do a few more to begin the class. And then we'll get to Lenz's law and the last equation we need. So this one says a 50-turn coil has a diameter of 15 centimeters. The coil is placed in a uniform magnetic field of magnitude 0.5 Tesla, so that the area vector and the magnetic field are parallel. Find the magnitude of the EMF, aka find the voltage in the coil if the magnetic field is reduced to zero uniformly in 0.1 seconds. So we got a loop, we got some fields. Who cares the direction of the field at this time? We're not too worried. Let's just say it's into the page. And we're trying to find the EMF. So we have N, this was our new variable. That was just how many loops you have. We have a diameter of 15 centimeters. Never in this class have we really used diameter for much, so let's just immediately recognize that we're going to convert that to radius. Radius is going to be 0.15 over 2, which is 0.075 meters. Magnitude of the magnetic field is 0.5 Tesla. And we recognize that that is our initial field, and we look very carefully and see that the magnetic field will be reduced to 0. How long will it take for that to happen? 0.1 seconds. Okay, if we need more things, we'll find more things. But for now, we've got a good amount of variables. Let's work with them. What are we solving for? The EMF, which we remember is just voltage. And our equation is the one from the last slide. EMF equals negative N times the change in BA cosine theta. That's the flux over the change in time. Which the change in time will always just be T. It'll always just be how much time has passed in the problem. I will never give you a problem where I'll say, find the change in flux, find the voltage produced between 1 and 5 seconds. It's not going to happen. So if you see time in the problem, know that that's going to be the change in time. All right. As always, I need more space, but we're basically we're almost at the plug and chug step. We're almost there. There's one last thing or two that we need to do first. In step 3, I'm going to go ahead and recognize that what is changing. I'm going to do a couple things here. The area is not changing. Nowhere does it say radius is getting smaller or it's getting bigger. That's the only kind of things that could pop up. The angle, also not changing. Nowhere does it say that it's rotating. If the angle is changing, that corresponds to a rotation. It's not rotating. So, in our angle here, like every problem again that we've kind of seen, the angle here is 0, cosine of 0 is 1, all is well in the world. What is changing is the magnetic field. And I'll write this one last time. We have a circle, the area is pi r squared. Hopefully by the end of this class, you all are pros at finding the area of a circle because we have had to do it so many times. Circles are nice. Physicists love circles, we love spheres. They're the most symmetrical of objects. Circle technically has infinite axes of symmetry. And then at this point, it's just plug and chug. We got in, we have R, we have the final field, we have the initial field, we have the time. Fairly straightforward. So the EMF equals negative 50 times pi times 0.075 squared times 0 minus 0.5 divided by 0.1. And you will realize that basically every problem I've given you all, the negatives kind of cancel out so you don't end up with a negative voltage. It's fairly purposeful. It's because I don't want you all worrying too much about that negative. There will not be an answer where I say find the EMF and it's a negative voltage. That in the problem set you won't see that. In the test you won't see that. In the quiz you won't see that. It'll always be a positive voltage, but I am using this negative sign because literally the next thing I teach you all, it has a meaning. There's a conceptual meaning to it, and we're going to see that today when we get to Lenz's law. So I want to keep including it because it conceptually means something. And so I've kind of wanted that to kind of just sit around so that when we see what it means, we're like, oh, okay, this wasn't out of nowhere. So 50 times pi times 0.075 squared times 0 minus 0.5, all divided by 0.1, comes out to a nice, beautiful voltage of 4.418 volts, positive. Something to note here, you look at this voltage and you're like, that seems like a nice number. The reason it's kind of nice is because our field is ridiculously large. 0.5 Tesla doesn't sound big. It is big. Very, very hard to make a field near 1 Tesla. I say very hard. You basically need superconductors. Superconducting wires. This is kind of a good time to mention that. It's not going to be tested. How do you make a strong magnetic field? You get a lot of current. How do you get a lot of current? You have very low resistance. The higher the resistance in your wire, the harder it is to get a high current. Superconducting wires have a resistance effectively of 0. So you can put a ton of current in them. That's what MRIs are. How do you make a superconductor? You make it super cold. MRIs are filled with liquid helium, which is positive 4 degrees Kelvin. 4 degrees above absolute 0. Cold. Very, very, very cold. It's hard to imagine how cold. It's like negative 500, it's negative 269 degrees Celsius. I think it's like negative 300 or 500 degrees. I don't know Fahrenheit. Anyway, there you go, EMF. All right, let's rotate things. Whoa, look at the loop, it's rotating. We'll do a problem like this. They're not as complicated as it looks. It'll be fairly straightforward. It's going to be just like what we've been doing. What would be the induced EMF if a loop of wire was rotating? What a great question. Let's do one about it. A coil of 1,000 turns encloses an area of 25 centimeters squared. That's going to definitely throw some people off because the unit conversion there is going to be fun. It is rotated in a 0.01 seconds from a position where its plane is parallel to Earth's magnetic field to one where its plane is perpendicular. I'm going to go ahead and just kind of change the wording here to make things a little bit more kosher, a bit more comfortable, where its area vector, let's stick with the terminology we've been using, where its area vector is parallel to one where its area vector is perpendicular. If the strength of the field is 6 times 10 to the minus 5 Tesla, what is the average EMF induced in the coil? Same setup. I'm going to go ahead and draw a quick picture of this though. We start with a loop. It doesn't say if it's a circle or a square, but who cares? It gives us the area, so our life is a little easier. Let's make it a circle because I like circles. So we start with a loop where the area vector and the magnetic field are all nice and lined up with each other. And then we rotate it 90 degrees such that they are now perpendicular to each other. So they were parallel, now they're perpendicular. When we set up our givens, this is going to come in. So N equals 1,000 turns. The area equals 25 centimeters squared. And this is where conversions, you have to be really careful with the areas here. Whenever you have a square, That doesn't mean you just need to move it the normal amount. You got to move it twice that amount. So if you're doing 25 centimeters, I'm actually going to jot this down up here. 25 centimeters to meters would be 0.25 meters. I move it 2 places. Well, centimeters squared means I have to do that twice. I need to move it not 2 places, but 4 places. Because I'm converting centimeters 2 times. That's what squared means. I'm converting centimeters once, centimeters again. You're not going to have to worry about anything like that in the test, but that is an important thing to remember. This may actually come up in your day-to-day life. If you're ever doing any building of anything with wood or at home and you measure stuff and you want to convert it from like inches to feet, same thing has to happen. So that is a helpful thing to know just from day-to-day stuff. But you don't need to know it. It's not going to happen on the test, so don't stress it too much. All right, t equals 0.01 seconds. Magnetic field is 6 e to the minus 5 Tesla. And here is where we get our interesting stuff. Our initial angle is 0. Our final angle is, and you can choose radians or degrees. I'm going to do degrees, just because we're probably more comfortable with that. Not 180, 90 degrees. You can pick your poison. It's going to get chucked into a sign. As long as your calculator's in the right mode, you'll be good to go. Yeah.
Is the area still meters squared?
Yes, good point. Meters squared. Thank you. Fix that up here as well. Spot on. All right. So you can see what's changing here. It's our angle. This is the last scenario. We've done changing field, we've done changing area, now we have changing angle. At this point, though, it's the same old, y'all. Same exact process. But showing you all 3 versions just so you have an idea of what they look like and aren't surprised if one sneaks up on you. All right, my given list is very large, so maybe a little bit uglier here, but that's fine. Step 2, what are we solving for? The voltage, aka EMF. What's our equation? The same one we've been using, negative N times the change in B, A cosine theta over time. What is actually changing here? B stays the same, area stays the same. Cosine theta final minus cosine theta initial. The angle's changing, so that's all you have to do. Cosine theta final minus cosine theta initial. Just like before, we had magnetic field final minus magnetic field initial, or if the area was changing, area final minus area initial. It's changed, you just subtract those two. You do not want to do cosine parentheses. Maybe it works out. You don't want to put that change inside the cosine. Let's just put it that way. Trying to think if it would work out. Doesn't matter whether it would or wouldn't. It wouldn't be the right thing to do anyway. So let's go ahead and plug things in. So the voltage is going to be negative times 1,000 times 6 e to the minus 5. Unfortunately, our voltage may end up being negative at the end. I told you all that never happened, but because I switched up the wording here, it happened. I think it's going to happen. Not a huge deal. Cosine of 90 minus cosine of 0 all over 0.01. Theta here was 0. Theta here was 90. Just so we have that nice picture show. And plug and chug, you get an answer. Let's see what that answer is. 1,000 times 6 e to the minus 5 times 0.0025. The cosine of 90 is going to be 0. Minus cosine of 0 is going to be 1. But you know what? Just to prove a point, I'm literally going to plug the entire thing in my calculator. That's the beautiful thing with this class, y'all. Once you have the final equation, you don't have to do any math in your head. Even if it's 2 plus 2. Let the calculator do 2 plus 2. Make it work for its pay. It doesn't get paid anything. And then you can check if your thing that you wrote in the calculator looks exactly like your paper. That's the beauty of it all. And look at that. Ooh, lucky me. The negatives do cancel out, and I get 0.015 volts. Word there for a second, but it all worked out in the end. Yeah.
Do you remember last class when I asked you about like the pi thing, like taking it as like a distributive property?
Yeah.
So in this one, we have to do cosine 90 individually.
Yes.
And then minus cosine
Yes.
0.
Yes.
We can't do,
No, you can't do cosine of 90 minus 0. I mean, it'll end up working out the same in this problem, honestly. You end up getting, you get 0 minus 1 here. If you did cosine of 90, you get, no, that definitely doesn't work. You get 0. Yeah, that's bad. No. You have to do the cosine 90 minus cosine 0. Yep. All right. So there you go. And just for funsies, you all don't need to know the stuff that's going to show up with this next slide, but I'm going to show it to you anyway. You don't need to know it, but I just want to mention it to you. So this is the average EMF. This is something you do need to do with a problem I just did. Yes, you should be able to do a problem like this. 100%. Make certain you're comfortable with this. The next slide, no. There's an equation that's going to pop up. You do not need to write it down. So this is the average EMF, the average voltage across that time period. So that's the average. This is the instantaneous voltage. Instantaneous voltage. How do we get this? Calculus. You take the derivative. When you take the derivative, you get that cosine turns to a sine, and you get this change in angle over change in time. We call that omega. It's called angular frequency. And the reason I wanted to show this to you all is because the voltage is changing with time, and it's changing with time like this. Which, if any of you know anything about electricity, this is what alternating current is. This is how alternating current is generated by generators. The voltage goes up and down, therefore the current goes up and down. This is how generators work. Remember at the very beginning of this lesson I said, in the back of your mind, so there's things, we can change the magnetic field, we can change the area, we can change the angle. In the real world, which one do we actually change? It's the angle. You can spin something really quick. That's what a generator is doing. A generator is literally spinning a coil really quickly in a magnetic field. Yep, I definitely trust the link that I posted in my own slide. Behold, it spins. And you can see here a magnet on top, magnet on bottom. You can see this voltage is changing with time. It goes up, it goes down, it goes up, it goes down. The faster I rotate it, not only do the frequency actually, I think, changes, but the amplitude changes as well. So you can generate a lot of voltage. This is what a generator does. This is what those giant wind turbines, they spins a coil in a magnetic field, makes voltage. Your generator, when you have gas running, it turns a coil in a magnetic field, makes voltage. Your car's alternator. You have a battery in your car that uses chemicals. How do you charge that battery? You have something called an alternator. An alternator in your car is a tiny little generator. That tiny little generator, as your car is running, gets spun, makes a voltage. It makes a voltage that charges your battery and keeps everything running. You can turn on your car, disconnect the battery, and your car will keep running. Your battery's only job is to get it kick-started. The alternator, your battery in your car is 12 volts. You can test if your car's alternator is working by measuring the voltage, and when your car's running, you should be reading about 14 volts because you need more than 12 to charge your battery. So again, fun facts galore. But this is how pretty much everything that produces electricity nowadays works. You make something spin. You make a spinning coil in a magnetic field. Coal power plants work the exact same as nuclear power plants. You heat up water, water turns to steam, steam makes something spin. How do you heat up that water? You either burn coal or you use uranium. The initial thing is just to heat up water. After that, it's all the same. Same thing with dams. Dams have water that come in and spin it. Pretty much all power generation, except for solar, uses this mechanism. So fairly important. Now you know. Spinning coils make voltage. All right. I'm not going to worry about this review question. So I told you all last time there's review questions sprinkled throughout here. What I'm going to do is when I post these answers, when I post these slides, I'll have the answers picked here for you. You can go back through these and practice and see if you can get that answer. For the sake of time, though, I'd rather get through the content and then kind of give you, hey, here are the main things you need to study. So I'm going to skip them for now, but when you look at these slides online later, they'll have the answers circled. Okay. This is one of the two things, you all, that we need to cover today. Lenz's law. I just told you we made a voltage. Lenz's law tells you the direction that current's going to flow because of it. Lenz's law says that the EMF, the voltage, will make a current. And it will make a current to oppose the change in flux. That's a whole bunch of jargon that may have made some sense to some of you. It'll make more sense as we practice it. I'll explain as we get through. A lot of jargon in here. A current will be induced to oppose the change in flux. That's kind of the mantra, and we'll explore that in some examples. I'll unpack that in a bit more detail. Another way you can think about this is it wants to keep the same amount of magnetic field lines in it. That's the way I like to think about these problems, and that's more so what I'll be talking about today when we solve these. Current, things don't like to change. That's basically the rule here. They don't want to change. So if there's a certain amount of field lines going through it, it doesn't want to lose those. So when it starts to change, it will make a current to try to keep it the same. This will make sense as we explore examples. So here's the strategy. First, you draw a picture of that magnetic field in the wire. Which way is the field pointed? How is the wire oriented? The loop of wire. It's always going to be a loop. Determine whether I'm getting more flux or less flux. More field lines or less field lines. And in what direction. Then, make a current. So I'm going to need to make a field that kind of reinforces what I'm either losing or opposes what I'm gaining. If I'm getting more, it wants to oppose it. If I'm getting less, it wants to gain more. Then we're going to use the right-hand rules to find the direction of current necessary to generate the field. Okay. A lot of fancy steps here. I say fancy steps. It sounds like a lot of steps here. It's actually fairly simple. The examples are going to make it more clear than this words. These words describe what we're doing. I want to make sure you see these words so that you can go back and kind of refresh it if you'd like. But really doing the examples is going to help the most. And I've introduced right-hand rule 2.5 to you before. I will remind you what it is because it makes your life so much easier for these problems. So I literally copy and pasted the slide for right-hand rule number 2 before, and here's what you do. I'm not going to even show you the words for it. I'll show you the words for it. Say I have a loop of wire. Bam, there's my loop of wire with current. If you want to find the direction of the magnetic field, it's this easy. Inside the loop, which is the only place we care about when it comes to flux, take your fingers, curl them around them, thumb points in the direction of the magnetic field. Done. It's the easiest rule to use. It's kind of a shortcut for 2. Take your fingers, curl them around in the direction the current's going. My thumb points out of the board. Done. So the magnetic field inside of this thing points out of the board. Fingers curl, thumb points there, easy peasy. If the current goes the other way, let's just draw that haphazardly down here. That doesn't make sense. Take my fingers, curl them that way. And my thumb now points into the board. Bam. If you have a loop and you want to find the magnetic field in it, this is what you do. Just curl your fingers in the current, thumb points in the direction of the field. Yeah?
For a point outside of the loop.
It'll be the opposite. Great question. For outside the loop, it's the opposite. The great news is, for the ones that we're about to do, for all this stuff with Lenz's law, we don't care about the outside, but that is true, and I'll go ahead and draw that on here just for clarity's sake. Outside it, it's the opposite. Inside it, you can find it super quick. Outside it, it's the opposite. For the Lenz's law stuff we're about to do, though, we won't have to worry about outside, but that is a great question. So, if you know the direction of current, turn your fingers around it, thumb tells you the field. If you know the field, Put your thumb in the direction of the field. Fingers tell you the direction of current. You can kind of go both ways here. So that top one, the field is outside of it. If you point your thumb outside of it, ta-da, my fingers go counterclockwise. That bottom one, if I put my thumb into it, my fingers go clockwise. So you can go either way. Yeah.
Is that because, like when you have a loop, the field is like going
Mm-hmm.
and then like...
Yep, it goes in it, and then it kind of sweeps around the outside and goes back in. Yeah. It's a great, that's why they're opposites, because it goes through the middle, sweeps around, and comes back in the other side. Okay, so the practice down here that we're about to get through, these are on the study guide. These are the ones that you're going to want to kind of practice through. I've kind of got every scenario here that can basically emerge. So we'll explore one at a time. We'll spend a good amount of time on the slide practicing it. I will literally do every single one with you all right now, and I will try to run around to both sides and do it online as well, webcam, all the things. So one at a time. Don't worry that there's 6 up here. We're just going to do A right now. In A, we have the loop here. There's my beautiful loop. It's the closed loop. Yes, I know there's some lines that go off it. We don't care. We only care about where it makes a closed loop. What we need to consider here, here's how you solve these problems. As my rod is moving to the left. So what's happening to my loop? Is it getting smaller or bigger? What do y'all think? It's getting smaller. Later on, it's over here. It's smaller. So, am I getting more field lines or less field lines? If it gets smaller, do I have more arrows? In these cases, the magnetic field is out of the page. Do I have more coming out of it or less coming out of it? You can clearly see here, if this is my new loop, there's less dots in it. There's less. I lost field lines. So, Lenz's law says this is why the negative sign was in Faraday's law. The negative sign says it's going to try to it's going to make a voltage to oppose the change. That's why that negative sign's there. I need to make a field to oppose this change. I don't want to lose field lines going out of the board. So, how do I do that? Well, I make some. I need to make more field lines going out of the page. Use that right-hand rule 2.5 to figure out the direction. Thumb in the direction of current, thumb in that direction, your fingers will curl in the direction of current. Done. Try it out, y'all. Point your thumb in the direction of that new magnetic field that it's going to make. Your fingers will curl nicely around, and it'll tell you whether you're clockwise or counterclockwise. At the end of the day, that's basically what all these problems, every single answer here will either be clockwise or counterclockwise. So, again, I'll kind of move around all boards. Right hand rule 2.5. Put my thumb there, and hold my fingers curl counterclockwise. Done. Over here, my thumb points the same thing. Thumb points this way. I wanted more because I was losing them. Counterclockwise. Online, my thumb points out of the board. Fingers curl counterclockwise. So which way does current flow in this situation? Counterclockwise. CCW. Yeah.
Will we ever see field lines as like X's to go like?
Sure. Yeah.
This way?
In that case, it would be the opposite. If I replaced all those dots with X's, it would do the exact opposite. Yep. So I can make up one of those as well pretty quickly. We'll have there's even some more that look differently. All right, next one. Same thought process. I have a loop leaving the field. Am I getting more of them or less of them? As it leaves that area, behold, it was here, now it's here. Did I get more or less? Less. Woo! So I need to make more. It wants to do the opposite of what's happening. I need to make more. Which way do I need to make more of? Well, they were that way, so the new ones better be that way. So, same thing. Thumb on the direction. Oh, look, it's also counterclockwise. I want to make more. I want to oppose the change. That's the name of the game, y'all. When it comes to Lenz's law, oppose the change. If I'm losing them, make more of them. If I'm making more of them, make less of them. And we're going to see how we make less of them in just a second. So this one is also counterclockwise. And to clarify, these dots are going to be B. If we ever see these dots, those are B, orange. I just don't have enough room to fit them in my beautiful, tiny little circles. So you may say to yourself, is it always counterclockwise? Let's do C. C is moving into a region. It went from a region of not having field lines to an area with field lines. Am I getting more or less? More. It doesn't want more. How do you oppose more? If it's getting more out of the page, you do the opposite. What's the opposite of out of the page? Into the page. How do you oppose that change? It makes field the other way to cancel them out. So it's going to make some field lines going into the page to cancel out that change. It doesn't want them. It was perfectly happy where it was at. Well, too bad, so sad. We need them. All right, so thumb points into the thing clockwise. Thumb points into the thing clockwise. Thumb points into the thing clockwise. CW for clockwise. All right, try the next one, y'all. I'm not going to say anything. In part D, go through the logic. Am I getting more field lines or less? If I'm getting more, cancel them. If I'm getting less, cancel that, make more of them. So as it's moving to the right, hopefully you recognize I'm getting more of them. Don't like it. Don't want them. Cancel them out. Make some into it. I don't want more. Same logic. If I need to make a field into it, clockwise, same thing. Put your thumb, fingers curl around. Life is good. All right, we'll do the last two scenarios, and then I'll make up a click. Well, I don't need to make up a clicker question. I already have one for the next thing. All right, next one, instead of something moving, the field is getting bigger. My reminder to you all, if the field is getting bigger, that means more field lines. That's the definition of a stronger field, is more field lines. So, the magnetic field here is increasing. The loop is very upset about this. It wants to oppose that change. So as time goes on, more of those blue dots are appearing. How do we get rid of those blue dots? Same way we got rid of them in the last situations. Don't want them. Don't need them. Get rid of them. I cancel it out. I was getting more out of the page. How do I cancel it out? I make more into the page. Clockwise current. I've got more going out of the page. I want more into the page to cancel it out. Clockwise. I'm getting more out of the page. I don't want them. And the next one is the exact opposite. I'm getting less field lines. Oh no. I'm devastated. My security. I'm losing dots. I want more dots. So I need to make more field lines in. All right, I need to make more field lines out because I'm losing them. Thumb points out, counterclockwise. Yes?
So is the trend whenever you lose is counterclockwise and the opposite?
Depends which way the field's pointed. If the field here was pointed the opposite. So the question was, is this always the trend? If I'm losing them, is it always counterclockwise? If I'm gaining them, is it always clockwise? Depends on if the field is out of the page, yes. If the field's into the page, the trend completely flips. Yep. So let's look at one where you don't even have dots and X's. I got a magnet. This magnet is getting closer to the loop here. It's getting closer to the loop. And as it gets closer, let's start the clicker thing so you can actually answer. And by start the clicker thing, I mean plug in my clicker thing and then start the clicker thing. So now you can have some nice time to deliberate and think. the north pole of a magnet is moved in. And this is a good problem. I will remind you, because we haven't reinforced it too much, magnetic fields point away from the north. I will remind you all of that. I'll even draw them on the picture here, because it's not something we've really mentioned that much. It doesn't really come up that much, so I'll give you that little hint. Magnetic field lines point away from the north. Okay? So the question to you is, as that gets closer, which way is current going to be produced? How will it generate current to oppose that change? Loops of wire are like cranky old men. They don't like change. They'll do everything in their power to oppose it. I don't know if that's a good analogy. Try it out. As it gets closer, what happens? Which way? Am I getting more field lines or less? If I'm getting more, in what direction? I need to oppose those if I'm getting more. If I'm getting less, I need to make more of them. Will it make a current clockwise? Will it make a current counterclockwise? Or will it not make a current at all? Is the flux not changing at all? If it's not changing at all, then who cares? It's happy. Nothing's changing, so it doesn't need to do any boycotting or anything. We'll go to about 140 on this. In 5, 4, 3, 2, 1. All right. So let's explore what's happening. Am I getting more field lines or am I getting less? Let me erase some of these hideous arrows. So as this thing gets closer, I'm going to kind of draw it off to the side. It is getting more field lines. Well, I would like to draw it, but in a different color. Oh, no. All right, it's getting more field lines. We're going to hit this beautiful save button. Everything is awful. All right, I just got to close it all down and restart it. I would love to save my work that I spent so hard on. As it gets closer, it's making more field lines down. As it gets closer, more field lines down. You get closer to a magnet, it gets stronger. So as I do so, worst comes to worst, I'll redraw this. Should I force it to do it out? How do I oppose it? If I'm getting more down, I need to make some up. The opposite direction. So, which way will current be? Do a little. I need some up, so I point my thumb up, and my fingers go counterclockwise. All right. I have to give it, I'm going to have to redraw it all. Devastating. Goodbye, PowerPoint. All right. Back we go. You all can see my beautiful organization in here. Oh, so lovely. Sneak peek behind the scenes. So, in this case, it would be counterclockwise to make that field up. Doing great. And while we're waiting for this, if the opposite was happening, oh, look at that. Maybe it saved it for us. Who can say? Oh, glorious. Look at that. Half the work I'll have to do. So the answer is counterclockwise. We'll draw a picture here. Why? We make field lines like this. As it gets closer, it's making more of them. Oh, so many. Terrifying. So I need to make some the other way. So current's going to flow counterclockwise to make that happen. Nice work. If you didn't get that, that's okay. Practice makes perfect. Practice makes permanent. All right. The North Pole, this is a nice one. I like this one. The North Pole is at a set distance from a copper loop, which is rotating as follows. This loop is just kind of like take a hula hoop and just kind of rotate it, kind of like a wheel. It's rotating like the wheel of your car. Will the induced current be clockwise, counterclockwise, or zero? No hints here. Am I getting more field lines in a certain direction and I need to oppose them? Am I getting less field lines in a certain direction and I need to oppose them? Or is the field line staying the same and I don't need to do anything? What's going on here? And again, to clarify this, it's rotating like a wheel on your car. And I just took your hands and kind of slide it around. Three-dimensional pictures are hard. We'll go to 120 for this one. And I can guarantee you, for good or for bad, there's a couple questions on the test where you need to be able to do this stuff. So, if you're wondering, will this show up on the exam? Yes. This is basically half of what I need you to remember from this week of stuff that we're covering. All right. 3, 2, 1. All right. So as this wheel spins, am I getting any more field lines? No. The magnet's not getting closer. It's not getting farther. The magnetic field lines are doing the same thing. The wheel's just spinning around. How can you prove that? If you looked at this, you closed your eyes, and I spun it, you would never know. That's an indication that nothing changed. So this one was kind of a tricky one. Doesn't change at all because the loop, the flux isn't changing. The magnetic field isn't changing. The area is not changing. And it may be tempting to think that the angle is changing, but remember that angle is with respect to that area vector. As I rotate that wheel, the area vector is still pointed the same way.
So if that were to like flip like...
Yes, if I took that thing, I lost my beautiful piece of carpet. If I took that loop and instead kind of rotated it like spinning a coin, then yes, it would generate it. But in this case, it wasn't spinning like a coin, it was spinning like a steering wheel. So, don't stress it too much, as long as you understand the idea. All right. This problem looks like it has a whole bunch of crazy stuff on it, but you can do this. I am literally just asking, what is the flux through this loop? Here's my loop. It's got this side is 3 meters long. This side is, the up and down is 2 meters long. The magnetic field is pointed into the page. It is 3 times 10 to the minus 6. What is the flux? What is the magnetic flux? There's a reason I'm asking you this. You may be like, this feels like we're going backwards. All will be made clear. And if you notice, all the units are different. So that also kind of could give you, I won't say anything more. Is the answer 2 times 10 to the 6 meters squared divided by Tesla? Is the answer 0 Webers? Is the answer 1.8 e to the minus 5 Tesla times meters squared? I'm going to change all these to those e's that we're familiar with. Or is it 5 times 10 to the minus 7 Tesla divided by meters squared? We'll go to 140. Maybe a little bit longer. Maybe 145. And 5, 4, 3, 2, 1. All right, so we remember way back when I defined flux, I defined flux as BA cosine theta. Area vector is parallel to the magnetic field. How do we know that? Take your pencil, put it on the thing, and point it out on the board. So it's either parallel or anti-parallel. Either way works out fine. The magnetic field is 3 times 10 to the minus 6, and it's a square, so the area is 3 times 2. 6 times 3 is 18. Do the math, comes out to 1.8 times 10 to the minus 5. And if you're clever, you can look at the units. The equation for this is magnetic field times area. The unit for magnetic field is Tesla. The unit for area is meters squared. So Tesla times meter squared is the unit for flux. It comes from the math. So there you go. Now, why did I give you all this problem? 1, wanted you to remember how to get flux, because it's important. 2, this is going to lead us into the next equation I'm going to show you, which is, first we have to think, what happens if I move the silver rod to the right? We kind of already seen this when we practiced our Lenz's law. As I move this to the right, I'm getting more field lines. As I move this rod to the right, you can see I got 2 more blue X's. I don't want 2 more blue X's. So a current will be induced. Where does that current come from? The EMF. If only we had a handy equation for that. We'll find that in a second. For now, practice. Lenz's law. If that rod is moving to the left, so I know I said to the right before, but now it's moving to the left. If it's moving to the left, which way will current flow? And let's scribble out this I here so we don't confuse anyone. If it's moving to the left, go through the thought process. Am I getting more field lines or am I getting less field lines? Whatever's happening, make it do the opposite. If I'm getting more, make field lines to oppose it the other way. If I'm getting less, make more to build it back up again. All right, we'll go to 130. And 5, 4, 3, 2, 1. All right, so here's the trick to this. Draw where the rod will be a little bit later. My loops got less. I lost X's. Devastating. All right, let's make some to build it up. I need to make more X's. I lost some. I used to have, if you just literally count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now I've got 9 X's in my loop. Here's my loop. I've only got 9. Used to have 11. So let's make a couple more. How do I make a couple more? Thumb into the page clockwise. I need to make more because I lost them. Thumb into the page clockwise. Thumb into the page clockwise. Thumb into the page clockwise. You can guess what would happen if the rod moved the other way. It'd make counterclockwise to oppose that increasing. So, definitely look over these. As always, y'all, my pro tip to practicing these problems, look at them without the answer. Every time you see the answer, your brain's going to automatically be biased towards that. The problem is during the test, I don't give you the answers. So, when you practice these, do it without the answer, then look at the answer. You can usually do that a good few times before your brain accidentally memorizes the answer. So, spread these out. These are good kind of flashcardy problems to do. If y'all look at the problem set, there is a whole bunch. These are literally the ones that I did today in class. And they're nice, and when you look at the one without the solutions, you can kind of go through these and try it. And oh look, fun. Another one of these as well. I think I'm actually going to solve that one with you all at the end of class. So, there you go. Another review question I'll give you the answer to later, but here's the punchline, y'all. Here's the quick derivation. My flux is changing. I know that looks like a derivative because it is. Magnetic flux is changing. Magnetic flux is BA cosine theta. Cosine theta is not changing. So I can pull out B. I can pull out cosine theta. I'm left with area. What is area? Length times width. Length times width. The length is not changing. The width is changing. So this is just a derivation. You don't need to know it. Length, width. I can pull out that length. So I get LB. And the change in W, the change in width over the change in time is velocity. Here's what you need to know. The EMF generated is BLV. B is the magnetic field. V is how fast it's moving. L, very, very important. You all don't mix up what L is. L is the length of that rod. L is here. I'm going to put a giant, this one, not this one. It's very tempting to use the other one because they're both in meters, not that one. The length is the length of the rod. That comes from the derivation. The length of the rod got pulled out. It's not changing. The one that is changing, the one that is responsible for velocity, is the width. So that's in the V. That width is in the equation. It's in the V. How fast it's moving. And good news, y'all, we're basically through it at this point. Got a couple more. I'll work through a problem. I should be able to have a few minutes at the end to kind of highlight, hey, here are the things you need to study for the test. If we do somehow run out of time today, and I'm not able to get to that, I will send out an announcement with a nice bullet point list of here are the things you need to be able to do for the test. So now a nice list of skills that you all need for the test. So that'll help you all with studying. I will also post an old note card as well, if you so desire that. It's kind of like a little cheat sheet kind of deal. All right. So let's apply this equation. Voltage equals BLV. Here's that problem. It's the only one in the problem set, but it is a very important problem to know how to do. Hint, hint, nudge, nudge. The rod below moves to the right on essentially zero resistance rails. Basically, always ignore friction. At a speed of V equals 3 meters per second. If the magnetic field is 0.75 Tesla everywhere in the region, and it's pointed out on the board as shown in the picture, what is the current through the 5 ohm resistor, and does the current circulate clockwise or counterclockwise? The picture's already here. Everything's already labeled for us. How kind. So I don't need to draw anything. I'm just going to go straight to writing down the givens. Velocity is 3 meters per second. Magnetic field is 0.75 Tesla. Make my pen a little thinner. The resistance is 5 ohms. That's weird. Why did I give resistance? All will be revealed. Maybe you can see ahead and see where it's going to come up. If you can, awesome. If not, that's okay. All right, what are we solving for? We are not solving for the EMF. We're not solving for aka voltage. We are solving for current. What equations are we going to use? Well, you can probably guess we're going to use the one that I just gave you. If you have a moving rod, immediately your mind should go to, I'm going to use EMF equals BLV. Current is nowhere in that equation. So this is where we have to remember EMF is the same as voltage. Do we remember an equation that relates voltage, current, and resistance? V equals IR, our old pal that you still need to know for the test because there's circuits involved. V equals IR, Ohm's law. Remember, EMF is voltage. Those variables don't look the same, but they are. It's called EMF because it is voltage, but it's due to different reasons. It's kind of weird. Don't worry about it too much. If you want to know the details, please feel free to come up and ask me, and I can give you the more details there. As far as you all need to know, EMF is voltage. Same thing. As far as when it comes to tests and stuff like that, that's the key information. That's what you need to remember. So copy and paste this on over. Put this up here, put our beautiful picture on in here. And it's just, I'm going to go ahead because I like to do this in step 3. I'm going to go ahead and put the variables in. So if I put these two together, I get IR equals BLV. Remember, EMF is voltage. So if EMF equals BLV and voltage equals IR, they equal each other. If you want, put a tiny little equal sign right there. They're the same thing. Solving for current, I get BLV over R. If you prefer, you could use the EMF one equals BLV, find the voltage, then plug it in, then do that. I like to just get one final equation with the variables because it makes my life a little easier. It makes it less likely that I make mistakes. There's a reason almost all physicists do this. It's just usually a little easier to do, and it's less likely you're going to make a silly mistake. But do whatever gets you the right answer. So I equals, we just plug in numbers, and it's fairly straightforward. Times the length, which is, forgot to put that up here. And this is the beauty of doing these problems, y'all. When you can figure out what you need to do, you can sometimes recognize, oh crap, I'm missing that variable. Look back at the problem and be like, there it is. It's at 4 centimeters, which is 0.04. E is 3, resistance is 5. And this problem is nice for a couple reasons. It incorporates a couple concepts, and it helps us to see that when we're making this EMF, it is making a current. How do you calculate the current? You divide it by the resistance in the wire. That's it. Every single time you all been solving for voltage in these problems, it's been making a current in those wires. You just couldn't calculate it because you didn't know the resistance. 0.018. And I'm going to pause here and see if you remember the unit for current. Because it's been a little while. It is amps. Good to remember these things. Amps, named after also called amperes, named after a guy whose last name was Ampere. Yeah.
So it's like voltage in terms of like V equals IR, or reference to like charge, and then like the other one is more reference to like magnetism.
It's more voltage is there's a potential difference. EMF, there's technically a potential difference, but the weird part is that it kind of experiences it everywhere. There's not like a part of the wire where it's like 12 and a part of the wire where it's 0. It kind of just experiences as if there's a 12 and a 0 difference everywhere. So that's the idea. Voltage, you have a high end and a low end. EMF, it's as if there's a high end and a low end, but you can't actually find them anywhere on the wire. But it's acting as if there is. All right. So, the last thing we need to cover for magnetism is a moving rod, which is almost the same. Well, I'm not going to spoil it. So, I have a moving rod. It's got charges in it. Protons, electrons. As it's moving through this, what are the charges that are allowed to move? Electrons. So let's just draw those. Who cares about the protons? They're stuck in place anywhere. Anyway, so there's a bunch of electrons. I want you all to use right-hand rule. So each of these electrons is moving to the right. This is good practice. Use right-hand rule number 1. What way will they move? I have negative charges moving to the right in a magnetic field pointed into the page. Which way will the force be on these charges? This is a great review problem that also we need to answer to understand the last little tiny bit. I have negative charges moving to the right with some velocity. What is the force they experience? What is the direction of the force? So right-hand rule number 1, you take your hand, my fingers point in the direction that they're moving, so they're moving to the right. My palm needs to point in the direction of the field, that's into the page. My thumb points up. And then we get really disappointed when we remember that these are negative charges and they do the opposite of that. These are going to move down. And this is they're going to move down because right-hand rule gives you for positive charges. These are negative charges. Hint, hint, nudge, nudge. You all need to remember that negative charges do the opposite. That's important, so don't just focus on positive charges. They're going to go down, which means as this rod moves through space, I get a bunch of negative charges built up down here. And where do those negative charges come from? The rest of the rod, which means this side is missing negative charges. And lo and behold, I have made a potential difference. One side's got a bunch of negatives, one side's got a bunch of positives. And here's the punchline. It's the same problem as the last one. It ends up being the exact same equation. The voltage that we generate from a moving rod through space, even though there's no wires, there's actually no current flowing through it, but there is a potential difference. If I connected wires, I would get a current. It is the voltage equals VLV. Exact same equation. And this is a really interesting case. It's interesting for a couple reasons, but one thing that's really interesting is they've actually, I'll get to it one of these later slides, they actually tried to use this to generate power in space. They had a satellite going around, they sent a really long wire with something at the end of it, and then it traveled through Earth's magnetic field, and it generated such a high voltage that it actually melted the wire. It ionized the particles around it, and it actually worked so well that the wire was super long, I think like a kilometer or something. So it's an interesting way of actually generating power. Generating voltage in space. You just have a super long wire. Practice. This is the scenario. I have a 20 kilometer long wire moving perpendicular to Earth's magnetic field, which is 5 × 10⁻⁵ Tesla, at a velocity of 10 kilometers per second. You can get going real fast in space. That means every second this thing was traveling 10 kilometers. This is a real situation. In space, you can go real fast. There's no air to slow you down. Every little bit of thrust from the rockets is conserved. Nothing slows down really in space once you get it going. So be very careful with these kilometers. And this is the last thing we need to cover, so I will have some time to do those kind of main points. These are the things to think about when you're studying this next week. Sadly, I won't have time to do the note card. We'll start that on Tuesday. We'll have plenty of time to get through the note card on Tuesday. All right, we'll go to like 220. Maybe a little bit longer. We'll say 230. Oh, like Harvard. Found it. All right. Give a few more seconds. Let's say 240. That's just as people responding. And 5, 4, 3, 2, 1. All right, so to write this out, what's given? I mean, I can draw a picture. There's my wire. It's flying through space in some velocity. The magnetic field is perpendicular to it. The givens are the length of the wire is 20 kilometers, which will be 20 e to the 3 meters. The magnetic field is 5 times 10 to the minus 5 Tesla, and the velocity is 10 kilometers per second, which we also need to convert, so that'll be 10 times 10 to the 3 meters per second. Our equation for the voltage was BLV, which comes out to 5 e to the minus 5 times 20 e to the 3 times 10 e to the 3. We got big numbers, we got small numbers. At the end of the day, we get 10,000 volts. It's very high. And, again, this is a real thing. There's a video. We won't watch it. Feel free to watch it later. You basically just see it get really bright because the voltage was 3.5 kilovolts. So this wire, so it was in the space shuttle. They sent a little satellite out and a super long wire. Inside that wire was a little bit of air. For some reason, don't exactly know why. That air got that high of voltage. That's how neon signs work. When you get a really high voltage and you put it through gas, it actually turns into a plasma, which is a very hot gas, and that got very hot, melted the wire, and it broke. So basically the video is this really bright line that's in space, and then it, breaks. So, interesting. Yeah?
So in the previous problem you just did, both the velocity and the length of the wire are in kilometers.
Yep.
So why did we convert them if they're both the same? Is it because of the units in Tesla?
It's because the units for volts. The way every equation in a physics class works is you have to have it in base units. So even though they're both in kilometer, they're being multiplied so the effects don't cancel out. So the way this equation works, epsilon equals BLV, everything has to be in base units. Length has to be in meters. Velocity has to be in meters per second. Magnetic field has to be in Tesla. And that's true of every equation we work with in this class. They're kind of like a machine, and you got to put in the machine a certain way, otherwise you won't get the expected result. Good question, though. All right, at the end here, nothing too special. It also works if you rotate it. Don't worry about what it is. But last thing I want to point out to you all, EMF is related to, this is an integral. I know it looks gross, yada, yada. Voltage is the electric field times distance. And this equals a change in flux that has to do with the magnetic field. Long story short, we have an equation that relates the electric field and the magnetic field. They're connected. That's why it's called this section, that's why electricity and magnetism are actually connected, even though they seem way different. Electric fields move charges one way, magnetic fields only do it if they're moving. They seem way different. But the fun fact I'll give you all, an electric field turns into a magnetic field if you're moving. An electric field will look like a magnetic field if you're moving. A magnetic field will look like an electric field if you kind of go the opposite direction. Depending on your frame of reference, it'll be an electric field or magnetic field. All right, let me give you all the quick rundown of what you need to know. I'll make it on here. Reminder, everything, so studying for test. One of the first, and I'll make this nicer, and I will send this out an announcement tomorrow. I'll make a much nicer bulleted list, but I just want to get your all's minds kind of reminded of everything we've covered. We have covered series and parallel circuits. Remember all the things we covered about that. We covered how in series, current is constant, in parallel, voltage is constant. We covered how to combine those into one resistor. Very important skills. Everything I just mentioned, things you need to know. We talked about forces on moving charges and current, which is another phrase for moving charges. You need to remember how to do that. You need to remember how to do right-hand rule number 1. Honestly, if I think anyone's going to... The biggest mistakes I expect to see on this test is regarding the right-hand rules. Practice, 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 y'all. You can look up, I have plenty of examples I've given. You can easily Google right-hand rule number 1, practice. You'll find a million problems online. They're basically, charge move this way, magnetic field move this way, find the force. We talked about things that make magnetic fields, sources of magnetic fields. There was a few scenarios. We had a wire, we had an arc of wire, we had a loop of wire, and we had a solenoid. And within all of these, we had right-hand rule number 2 to find the direction. So we found how to calculate the field due to a wire, an arc of wire, a loop of wire, and a solenoid. Key thing with a solenoid, distance didn't matter. The field was the same everywhere inside it, no matter how big that circle was. Hint, hint, nudge, nudge. You all saw a problem like that with capacitors on the first test. Solenoids, who knows? Then we just talked about Faraday's law and Lenz's law. Lenz's law. I feel like I'm spelling his name wrong, but I'll fix it later. So, changing magnetic flux makes a voltage. These are kind of the big overarching themes that have emerged. Basically, I just took each week of content we've covered. I will make a more detailed list with the specific skills you need. So I'll kind of unpack each of these. What do you need to remember in series and parallel? What do you need to remember in forces? What do you need to remember for forces? What do you need to remember for sources? What do you need to remember for Faraday's law and Lenz's law? When it comes to magnetic field, it basically boils down to you need to remember the equations and you need to remember how to do the right-hand rules for all of these. That's key. When it comes to series and parallel circuits, you need to remember that series current is constant, parallel voltage is constant, and how to take a big circuit and reduce it to a single resistor. Very key, very important. And that's basically it. This is everything we've covered. This is the stuff we're focusing on. Look through the quizzes, look through the problem sets, look through all the rest. Yeah, in the back.
Do we need to find current across circuits?
Yes. You do need to remember V equals IR. V equals IR is definitely going to come up in series. Could be a series circuit. Could be a parallel circuit. Remember how to find that if I give you a circuit with 2 resistors in series, how do you get the current? If I give you a circuit in parallel, how do you get the current? If I give you a circuit in series, how do you get the voltage of each one? If I give you a circuit in parallel, how do you get the voltage in them? Basically, take those ones with all the resistors and be able to go down to the beginning one and go back to the outside one. You should be able to do all the problems in the problem set, especially these last ones. These last ones here. Should be able to do all of these. That's the way to study problems like that, or these ones specifically. Alright, of course I'll be around for any questions. If you have any more questions, feel free to hit me up. Got 2 minutes in class, but if you have questions, email me, etc. Tuesday I'll make this note card. I will also send out an example note card that's not as nice as the one I'll do on Tuesday, but it's something to go off of for now. That way you're not waiting till Tuesday to figure out all the equations. Alright, if you're online, please shoot me an email if you have any questions. That's the best way to get a response from me.